Hello, welcome back to the channel. Let's look at another challenge today. So today's challenge is from LeetCode number 2852, sum of remoteness of all cells. So let's see what the problem statement is. So we are given a zero-indexed matrix grid of order n times n. Each cell in this matrix has a value grid I in j, which is either a positive integer or -1, representing a blocked cell. You can move from a non-blocked cell to any non-blocked cell that shares an edge. For any cell ij, we represent its remoteness as ri and j, which is defined as the following. If the cell ij is non-blocked cell, rij is the sum of the values grid xy such that there is no path from non-blocked cell xy to the cell ij. For blocked cells, rij is equal to 0. And we need to return the sum of all this rij over all cells. So let's see what the problem is really asking. So we are given this grid. So all of the black squares, they are -1 in the matrix or in the grid, and we are given this 1, 5, and 4, and 3. Some cells which are not blocked, right? And we need to return the sum of all the remoteness r and ij, right? Rij. So before we can look at this problem statement in the whiteboard, before we just go there, let's just look at the constraints. So the constraints, we have a n, which is it's a square grid. N can range from 1 to 300. And each element of grid ij, it can range from 1 to 10 power 6. Or if it's blocked cell, it can range, it's -1, right? So now we can look at this examples in the whiteboard. Okay, so this is the first example. Let's look at this the first example. So all of these blocked cells, black cells, they are -1. In the matrix, they are given as -1. We are given this non-blocked cells. Here is 1, 4, 3, and 5. So what we are being asked, we need to see the remoteness. We need to compute the remoteness for, let's say, this cell. How we get the remoteness of the cell is we get the sum, we compute the sum of all the cells, all of the non-blocked cells that are not sharing borders with this cell. What it means. So for this to get the remoteness for this one, which cells are not really touching with it, right? Just 5 is not touching, 4 and 3, right? Basically, to get this remote, to compute the remoteness of 1, we do 5 plus 4 plus 3, right? And this will be 12, and we just replace 12, right? Instead of 1. And for the 5, it's the same thing, 1 plus 4 plus 3. And if we just add, that will be 8, right? And for 4, we can compute this one, right? We can compute 1 plus 5 plus 3, right? So that sums up to be 9. For 3, 1 plus 4 plus 5, right? So that will sum up to 10, right? Which is this. And what we are being asked, we need to get the sum of all of this, right? Which is 12 plus 9 plus 10 plus this, and 15 and 20, it will be, we need to return 39, right? So this will be the response that we need to return. So let's look at another example. From this example, we can just say, oh yeah, what we can do, we can simply compute this the sum of all the cells that are not touching the cell, right? Which is like, it's simple, right? As long as they are, you may think that we can just compute all of the cells other than this one, right? Sum of all of the cells, like 4 plus 5, and just sum and replace this, right? And it sounds this very interesting that we can use that approach, but it may not work all the time. We should make sure that all of the cells that we are getting the values, they should not be in the same connected part, right? Let's see in the second example. For example, in this example, to get the remoteness of 3, you may think, oh, well, I can just simply get 3 plus 4, right? That will be 7. And replace this one with 7. Which doesn't work because we cannot add the 4 because 4 is it's touching this grade, right? The cell 3. So we need to make sure that the cell that we are getting the values, there should not be any path from this cell to this cell, right? But here, from this 4, there is a direct path to 3. So to get the remoteness of 3, we cannot account this one, right? We cannot count this one. We can only count this 3. So we can then, in that case, we can replace this 3 with this value, this 4 with this value, right? And this 3, which are the cells that are not touching this, it is this 2, right? And we can replace this by 7. So basically, total remoteness that we need to return is 3 plus 3 plus 7, right? And that will be 13, right? So I hope the problem statement is clear. So basically, from the second example, what we need to do, we need to see which cells share, which cells are in the same connected part in the grid, right? So this cell is in the same connected part with this cell. And this cell is separate, right? This cell doesn't have anything. But, there may be a case where there may be another cell which is 5, right? So this 3 cells, they are in one connected cells, right? And this one is in a separate cell, right? So what do you think? What we can do? So what we can do here, we can we can initially compute the total sum of all the grid values, right? So total sum, we iterate this through the grid, and we compute the total sum. Total sum will be total is basically 1 plus 4 plus 5 plus 3. It will be 13, right? 13. So then we need to, this is total. Then how we can compute this one, right? This 12. To get the 12, from this total sum, we subtract the value of the cell. So 13 minus 1 is basically 12, right? And here, total is 13. From 13 minus 4, it will be 9. 13 minus 3 is 10. And 13 minus 5 is 8, right? So this is a case when all of the cells are kind of disconnected, right? They are all unique in their own cell, which is like simple, right? But let's say this instead of this blocked cells, there can be two, right? Let's say this three cells, they are now connected. To get the remoteness for one, and right now the total sum will be 13 plus 2, right? It will be 15, right? Total sum will be 15. So for that, we cannot simply subtract the value of the cell. What we need to do, we need to compute the sum of this connected component, because this is the one that we cannot use to compute the remoteness, right? To compute the remoteness of this, we can only do 5 plus 3, and it will be 8, right? And 2 and 4 we cannot use, right? So that's why what we need to do, we need to compute. We need to compute. Let's say this is 2. We need to compute the total sum for each connected component. The connected component of the cells within this connected component is 1, 2, and 4, right? These are the values, but the cell number is, what is the cell number? 0, 1, right? 0, 1. And this one is 0, 2. And this one is 1, 2, right? This 0, 1, 0, 2, and 1, 2, they are the part of one component. And we need to create the components, the list, right? Let's say components list. Components list. In this list, what we are going to do, we will just say, okay, 0, 1, and 0, 2, and 1, 2. Then we also, this will become the tuple, right? We can just save them, and we will just store their total sum, right? Total sum 1 plus 2 plus 4. 1 plus total will be 7, right? So for all of the cells, that's what we do. And to compute the total remoteness for 1, in this case, and the total sum is 15. And to get the remoteness of this, and the sum of this component is 7, right? That's 7. Then total sum is 15. To get the remoteness of this one, so we are going to do 15 minus total sum of the component, right? So for that, we will need to do the traversal of the grid, where we can identify the cells that belong to the same component, right? Let's say for this is 1, and for this one, so we can say this is 2. For this component, we need to be traversing this grid to identify the members of each component. This is one component. This is we can also say there is a 6. So this is another component, right? And this will be one component. This will be another component, right? So what we will need to do, we will need to traverse in this grid. Either we can do this grid traversal, we can use the depth first search or breadth first search. I think that it will be BFS will be ideal candidate to do this traversal, what we need to do, we are going to identify what each so what are the members of this connected component, right? For this connected component, it will be 0 1 0 2 and 1 2, and their sum will be 7, right? So that's how we're gonna keep storing this. Then for the second one, component, it will be, this will be 1 0, so 1 0, and let's say this also exists, it will be 2 0, and this will be 2 1, right? 2 1, and their sum will be 11 and 14. Imagine this is not empty cell. So and there's we'll just keep this one, and 14 will be their sum. So after traversing this grid with BFS, we collect all of these components, right? All of the components with the corresponding sum for the component, right? So now what we will need to do, we need to iterate. We need to iterate this for this list, right? We need to iterate for this list, and let's say the length of this one, right? For this, let's say for the first cell, let's say, yeah, for the first cell, we need to get this 14, right? And for this one, we need to replace it with 14. For this one, we need to replace with 14, right? This is a total sum of the remote components. They are 14. And for each one of these, we will need to replace with 14, right? Let's say, this will be 2. And for each one of them, this will be 14, the total sum, and this will be 7, right? For each one of them, we will need to replace this with 7 and 7, and this will be 7 too. And for each one of them, the total sum of this is 14, so we will need to replace this with 14, this with 14, this with 14, and just sum all of them, right? And that's how we're going to return. So I hope this is the logic is clear. So we basically have to get the total sum. We're going to just iterate once through the grid, get the total sum. Then after that, we iterate the second time. In the second time, we are going to traverse to identify the members of each and the cells of belonging to the same component, right? Then after we create this components list, then we are gonna go iterate through this one, through this list, and to get to compute the total remoteness of entire grid, right? Let's see this in the code. So initially, we are going to compute the total rows and total columns of the grid. Then to do the BFS traversal, we need to say create the additional grid with the same size, where we can, it basically shows that if we have already visited the cell, right? Because we don't want to go into the endless loop of going over all the cells if we have already visited, right? Then step 1, we are going to get the total sum of all non-blocked cells, right? For that, we're going to go through this number of rows and the number of columns. And if the grid is not -1, because -1, that shows that grid is blocked, right? Then after we get this total sum, Then here in the step 2, we are going to identify all connected components in the grid, and we are going to collect them in this components list. So we basically do another iteration. So for this iteration, for rows, all the rows, and through all the rows and columns, and we say if the grid is not -1, which means the grid is not blocked and the grid is not visited. We have to check. We have to make sure that the grid is not blocked and grid is not visited yet. Then from that, we are going to run this BFS to do to return the all the cells of the specific component and its corresponding component sum. For the component within the grid, what is the sum, right? Total sum. And we are going to append this component cell and the component sum back to the components list, right? So this component sum and components list, it will be returning the all the cells and their corresponding total sum, right? The corresponding component sum, right? Then we say now we're gonna go through the BFS in the last step. Basically, then here result, we're gonna initialize result is 0, and we are going to iterate through this the components list where it has all the cells with its component sum, right? And for all the component cells and component sum is the components. And for the remote sum, we are gonna get the remote sum is basically total sum minus the component sum. Okay, because the component sum, because total sum is the total sum is the total sum of all the grid values, and the component sum is the sum of the component, because we cannot, because since those components are already touching that specific cell, we cannot account for we cannot use their values, right? That's why we need to subtract the sum of the component, right? Then, because if the component has 3 values, like 3 non-blocked cells, then we have to basically get we have to multiply that length of the cell, right? Of the number of non-blocked cells to the remote sum, and add to the result and return the result. So then let's see the BFS that basically identifies all of the connected components. So for the BFS, it's a typical BFS with a queue. From the grid, from the specific cell, we can go to into 4 directions, and we identify this for this is this one. The first one is right, right one, left one. Then we get the rows and columns again, because I did not want to just call with self, and we add that cell to the queue. And if the components then initial component cell, we're going to initialize to be empty list, and the component sum is 0. Then after we pop, after we add this to the queue, then we say that that specific cell is visited. Now we're going to perform the BFS to identify all of the connected cells to this specific cell. So for that, we're going to pop that row and column. Then we add the value to the component sum, and that specific row and column we add to the connected cells. And we go into 4 directions because we can go into 4 directions: left, right, top, and bottom, and number of rows. I mean the new row and new column. That's how we compute here. So we can go into 4 directions. We compute this new row and new column by adding that direction: row plus delta row, and column plus delta that additional direction. Then we check if that row and the new row and new column, they are within the range of the grid, within the boundaries of the grid. If the new row is between 0 and rows and new column is between 0 and columns, and we make sure that it's not blocked cell. If it's blocked cell, we cannot use that cell. If the grid new row and new column is not -1, and at the same time that the non-blocked cell should not be visited, right? If it's visited, then we cannot use it. Then we mark that new row and new column as true, which means it's visited. So now next time when we come, we will not visit that again. Then we add that, we append that new row and new column. If it satisfies with these conditions, then we add them to the queue. Then after we just finish identifying all of the connected cells of the component, then we return this component cells and its component sum, right? What's this total sum of the component? And this BFS will basically come back here. This will be running for all the cells and all of the non-visited cells. If this cell is visited, then which means that we have already covered that cell in the previous iteration, right? Basically, time and space complexity of this I will discuss in the whiteboard. So time and space complexity is, since it's a square grid, it is n times n, which is O of n square. Space complexity is going to be n times n, which is O of n square. Yeah, I hope this explanation is clear. And yeah, it's a little long, but and I just wanted to take time to really explain this with the code and with the whiteboard, right? In this case, Blackboard. Okay, thank you, and I'll see you guys in the next video. And please share your comments if you have any questions. Thank you.